So let's talk Cavendish's experiment. Cavendish's experiment was a nice way to illustrate that real objects, not theoretical objects, had a force of attraction, mutual attraction, acting between them. What he did was, he set up a mechanical system with a torsion spring up at the top, and it's kind of like a three-dimensional dumbbell with a mass at one end and a mass at the other end. And we really do have to think three-dimensionally here. So in the foreground, I want to put a great big mass here. I'm going to call it mass B. And make sure that we can see that it's in the foreground. And in the background, I want to put a great big mass. I'm going to call this one mass A. Mass B in the foreground, mass A in the background. I do want to say that mass A and mass B are equal to each other in size. I also want to say that mass 1 and mass 2 are equal to each other. And on top of that, I'd like to say that mass 1 and mass 2 are huge. Much bigger than a kilogram. And mass A and mass B also absolutely enormous. Okay? So these things are in balance with one another. So it's a nice balanced torsion rod with mass on either end. And masses just in front of mass 2 on the right and mass just below or just behind mass 1 on the left. So you sort of ask the question, what's going to happen to this thing? Well, if it's a torsion spring, then you can guess that there's going to be some torquing. So torquing means twisting, and if we have torque equals R times F, torque is actually a way of measuring how much force is acting a certain distance away from the center of rotation. Okay, so Cavendish was able to figure out how much force was acting between these two masses, given that they were a certain way, a distance away from the torsion rod, the vertical hanging torsion rod. Anyways, having said that, he was really just making force measurements. Now I want to make sure that everybody can understand what's happening here. If I look at the same situation from overhead, this is the overhead view of the exact same scenario. I've got my torsion rod here, vertically hanging, looking at it from overhead. I've got mass 1 on one end of the rod, mass 2 on the other end of the rod, and I've got A being attracted to 1, and B and mass 2 also being attracted. Now, these guys are attracted, and initially they sit at a distance R away from each other. And when I say a distance R away from each other, hopefully everybody understands by now that a distance apart really means the distance between their centers of mass. Not between their surfaces, but between their actual centers of mass. That's what that R value means. Anyway, over time and with meticulous observations and understanding how torque works, Cavendish was able to build up a set of data. He started taking a look at all the force measurements that he got out of this twisting system. He modified mass A and mass B, kept keeping them the same, modified mass 1 and 2, keeping them the same, and then he tried starting the masses at different distances away from one another. And you can build up a lot of data from this. Well, first of all, let's just talk about varying the masses but keeping a constant R value. So keeping the R value, the initial R value, as a control variable, and mapping out all the F values for all the different combinations of masses, that would be multiplied together to make a product, you actually build up a whole bunch of data that looks something like this. Beautiful, absolutely gorgeous line of best fit, totally linear. That's actually kind of sweet. And people start to think, well, he's really onto something here. I mean, you can just imagine Cavendish getting excited about this. Next thing, he starts messing about with the radius, but keeping the masses as control variables. And lo and behold, he didn't get a 1 over R proportionality, he actually ended up getting a 1 over R squared proportionality. And we can talk about the geometric argument for that later. But kind of neat, if you took the masses, kept them constant, and just messed around with the R value, it turns out that if you calculated 1 over R squared for every R value, and you compare that to the force due to gravity that was actually measured, again, you get this really sweetheart, scatter plot, but with the line of best fit applied, beautiful linear relationship. Absolutely gorgeous. Going through the origin for both of these graphs. So he figures, well, why not put these two things together? We've got our our radius relationship, our distance between centers of mass relationship. We've got our product of masses relationship. What if we put those together into one big relationship? And every time I do this experiment, I calculate mass A times mass 1 and divide it by r squared, the distance between the centers of the masses. Remember, when I'm talking about mass A and mass 1, it's just as easy to talk about these guys over here as it would be to talk about these guys over here, because it's going to be an identical force, since mass 2 and mass 1 are identical and mass B and mass A are identical to one another. Anyway, makes the measurements, and what do you know? You get a beautiful linear graph again. Except this time the y-axis is the force measurement and the x-axis is the calculated value, mass A times mass B, divided by r squared. Sorry, I shouldn't say mass A times mass B. Mass A times mass 1. That's the way I set this up. Mass A times mass 1 divided by r squared. Again, where r is the distance between the centers of the two masses. You say, well, great, it's a linear relationship. Well, darn right, it is great. Because let's take a look at what we can do with this. If we know that we've got a linear relationship for any pair of masses at any distance apart, when we multiply this whole thing together and divide by r squared, what do you do with a linear relationship? Well, why not find the slope? Turns out that when you find the slope for varying mass 1, mass A, and r values, the slope is always constant. That's what linear means, always constant. We get a rise over run value of 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared. And if this is the relationship that you get for every combination of mass A, mass 1, and r squared values, let's just think for a minute about that. Everybody knows, if you've taken early math, y equals mx plus b. Well, notice that all of our relationships, or all of our graphs, had a 0 as the y-intercept. So that b term disappears right away. Y equals mx then. Well, what's the m value here? Well, we just said that the slope is a constant in this situation. It's 6.67 times 10 to the power of negative 11 Newton. We'll throw in the units, meters squared per kilogram squared. What was the x again? Let's take a look at the axis. It was mass A times mass B all over r squared. And what was the y again? Oh yeah, force due to gravity. Well, this kind of looks like we have an equation. It's not just a relationship anymore. That's a beautiful y equals mx plus b equation. Now, it's a little bit dressed up, it's a little bit fancy, but this is a y equals mx plus b equation that relates the force due to gravity mutually experienced by, two masses at a certain separation. This constant is really amazing. That's a really valuable piece of information that we just pulled out of hanging some masses near some other masses. I want to make sure that we check the units though. Rise over run, for that graph that we were just looking at, would be, make sure that we get this right, rise would be the force values. The run would be mass A times mass 1 divided by r squared. So if I start simplifying this, and I'll show you what I did going from this line down to this line, I've got a denominator here that's a fraction, so I invert it and multiply. So it would be force over 1 times r squared, see that's the denominator in my fraction, divided by mass A times mass 1. If I simplify that just a little bit more, I end up getting, I'll just slide this off to the side here, a slope with units of, and we'll sub in our units at this point, so instead of saying force, I'm going to say newtons, and instead of saying r squared, I'm going to say meters squared, putting in our units, instead of saying mass times mass, kilogram times kilogram, and I get units of Newton meter squared per kilogram squared, which is what we said before, but we've sort of talked through how we know what those units have to be. So for a slope of force due to gravity versus mass A times mass 1 divided by r squared, where I've chosen to change the masses and the r's, you always end up getting a slope of 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared, and we call this constant g. And it's called Newton's universal gravitational constant, but Cavendish should get the credit for the work.